morning. It's my pleasure to introduce Professor Wieslaw Kubis from the Institute of Mathematics of the Czech Academy of Science. His research is mainly on general topology, function analysis, and mathematical logic and foundations. One of his current research projects deals with universal homogeneous objects in the context of category theory. And related with this project is this plenary talk on universal topological vector space.
Yeah.
Please, Professor.
Okay. Thank you. Thank you. So, in fact, the title is wrong, but I'm not interested in universality so much this time. Because I'm somehow affiliated with the topology in functional analysis section, yeah, so that's why this title. But after all, I'm going to talk about something very general, and yeah, should I use the keyboard? So, it's just an excuse, but you know, you search in the internet for evolution systems, there is no precise mathematical definition. Simply doesn't exist, but it's about category theory. So, but I prepared, the beginning of my talk is prepared for people who do not know category theory or do not like category theory or simply do not work in category theory. So, this is the setup I'm going to work with. So, you have some states or objects and transitions, which are arrows. Yeah, so, but why I call it evolution system? Because I'm interested in the, okay, you know, what happens when you move upwards, okay? So, I mean, you have arrows which make the states more complicated, yeah, or the objects more complicated. So, for instance, you could think of, let's say, all possible sets and all possible mappings, yeah? But then you may have a large set, and by using a mapping, you can go to a singleton, yeah? It's not what I like, so, but if you allow one-to-one mappings, it's okay, yeah? I mean, it makes more sense. So, in any case, this is just for, you know, for information. So, given, yeah, this is really category theory what I'm presenting now, yeah? So, we need some, we are talking about some objects which encode some possible states of some system, and arrows are or transitions, yeah? So should be nothing surprising after all. Okay, so comparing to automata, I mean, different from automata theory, I mean, transitions can be composed. You have composition, yeah? So actually, you do not need to know what a category is, yeah? Still, these definitions are sufficient. So, yeah, a composition operation is supposed to be associative, yeah? With the usual meaning, there's nothing special. And, okay, I didn't put anything about identity arrows because they are not so important, so that's it, yeah, for the moment. Now, all right, so, well, in this theory of generic objects, I'm going to present, things become simpler when you assume that there is some initial state where you start the evolution, yeah? So, again, let me repeat. So I'm interested in a situation where you have some system like this, or really a fixed category, and you build some sequence, yeah, which I will call evolution for some time. And I'm interested in objects which occur as limits, yeah, of this. So in any case, this is this initial state is formally a weakly initial object. Yeah? I mean, an object such that to any other there is at least one arrow, one transition. Right? So this is it, and now an evolution formally is a functor from the category of the natural numbers, yeah? But this is how I present it here, again, for people who do not know category theory. So you start with some, you start with the initial state, you choose some transformation or transition or arrow morphism, whatever, yeah, you arrive at some x1, then you continue with choosing another one, etc. And by this way you build an infinite sequence. Okay, so this is important because I'm going to describe some game playing with these things. Yeah. All right. And a piece of notation. Yeah, where the objects or states are denoted by capital letters, and the transitions are denoted by small letters with the same X. Yeah, like here. Okay, and the whole sequence or evolution will be denoted by X vector. Okay, we'll see it later. So of course this is the composition should behave in this way. Yes. So there's no randomness really. Okay. Now, one of the crucial properties. My colleague Tomasz Kania suggested to call it absorption property. So, what is it? You have such a sequence which encodes some possible evolution of the system, and the absorption property means that you go out from some, okay, maybe I have a diagram after all, yeah? I have a diagram here. You go out from some UN, you're always able to come back. And why I say, okay, in my talk, at this point, there are no precise definitions, okay? What does it mean, approximates? So, you can read it, okay, it equals, yeah? G composition F equals U and M. This is okay, fine, but in some cases you cannot achieve this. I mean, you really make some errors. I mean, epsilon error. I mean, you are given some epsilon positive, and you ask for each particular F, you ask for the existence of some G, such that the composition is epsilon close to this U and M. So if I want to be really formal, this should be a category enriched over metric spaces where you really have distances. But I simply do not want to go into these technical details. It's not so important. You will see it by examples. So, and this is the crucial property. It could be, yeah, generalized maybe in okay, never mind. Let's leave it as it is. Now, an isomorphism. Well, not so many blackboards here, that's the problem. So, because I wanted to draw some pictures, so, and I can use this, I guess, yeah? So, okay. Fine. And yeah, some markers. So, because you see, in this definition, everything is hopefully correct, but you don't see what happens. Yes, so you have one sequence and another sequence. So first of all, what's a transformation from this one to this one? It's okay. It has these objects on the way. So these are some arrows going maybe this way, huh? Not necessarily horizontal. If it is horizontal, this would be called a natural transformation. But there is this function phi and another one psi. So what does it mean? Let's say it goes from xn, and then this is y phi of n, okay? And it's supposed, it's called an isomorphism if you actually can come back, yeah? So you have, let's say, this one, which goes from here to some x. That is why there is this composition, psi phi of n, yeah? And the compositions should be equal to the transitions from the sequence. So think of the category of sets where these arrows are embeddings. So you really have two chains of sets, or even better, maybe some structures, some models, yeah? So sets with some extra structure. So this property and also the other one, yes, that going this way and this way is the same as going directly. It really tells you that the unions of these chains are isomorphic, yeah? I mean, it leads to an isomorphism. So, is it okay if I leave it here for this screen? Okay, so that's this, put this very abstract definition, but is apparently enough for describing things after. Aha, okay, so this phi and psi are increasing. So the collection of transformations or arrows, yeah, Fn, is formally a natural transformation from x vector to y vector composed with phi, yeah, I mean to a subsequence, and vice versa, the same for the other. So I simply want to talk about sequences or evolutions up to isomorphisms. So this is very important, yeah, to have this notion of isomorphism. And in practice, in all examples, you actually have a bigger category where everything, I mean, these sequences lead to some formally co-limits. Yeah. All right, so this is it, yeah, and yeah, so this is what I already said, so I can skip it, yeah. Evolution system is nothing but a category where you have a weakly initial object, a starting point, yeah, of any evolution. Evolutions are just functors. The natural numbers is a category where it's a partially ordered set of actually linearly ordered set, because you see the set of the natural numbers is also a semi-group, so could be a monoid. It's also a category, but I mean here as a linearly ordered set. So from, say, 1001 to 2018, you have a unique arrow, yeah, going this direction. Okay, so here is the crucial property needed for the existence of some special objects after, which will be defined a bit later. Yeah? So the amalgamation property, you can either read this text or look at the diagram. Actually, this maybe. See, so you this actually very well known in model theory. Yeah? So algebra, less known maybe in topology. So, and there will be some topology later. So you start with some object Z, or state or object. Yeah? You have two transitions F and G. You are always, so the amalgamation tells you that you are always able to continue these transitions by some F prime, G prime, so that not only the resulting state is the same, yeah, but also the transitions become equal. Yeah. So, well, if you take the category of sets with embeddings, one-to-one mappings, that's quite clear that it holds, yeah. Because what you take, yeah, definitely it would be good to some examples. So, yeah, if you have not only sets, but possibly sets with some structures. So this is the starting point, and the two transitions give you some extensions, yeah? So X, and then another one, call it Y, yeah? For purpose, I drew the picture in such a way that the intersection of X and Y is precisely Z. Yeah? And if these are just sets, you take the union. Yes, W is the union, X union Y. Yeah? If these are graphs, for instance, finite or whatever, infinite graphs, what you can do, you can still take the union, and let's say there are no new edges. Yeah? So you leave the edges between here, and you do not add anything. This is called free amalgamation. Now, if these are partially ordered sets, you have to do something, you have some work, yeah, because the union of these two partial orders is not a partial order, but you can close it to a partial order. It still works. And there are situations that it doesn't work. Okay, let's say another example. Let's say these are finite groups. What do you do? The union is not a group. You have to generate a group, and if you generate it in the free way, you actually get an infinite group. And if we want finite groups, it's not so clear. But there's a positive result that the amalgamation holds in the category of finite groups. So it will be mentioned later because of Hall's group. So I just wanted to point out that sometimes, very often, the amalgamation property is trivial. You just check it and you write a one-line proof. But in case of especially algebraic structures, it could be quite complicated or simply false. All right, so the Banach-Mazur game, it's not what you expect, perhaps. It's not about open sets, still no topology. Okay, so I should say the abstract Banach-Mazur game. So, yeah, so now I use a little bit of the formalism, fixed category or evolution system, if you prefer. And what is the Banach-Mazur game? Bm of k, where k is this fixed category. So there are two players. I decided to give them names, Eve and would be Adam. Odd because of odd numbers, yeah. Never mind. So player 1, player 2. But if it is Eve, then okay. Eve starts the game, yeah, it's written. So I guess the definition is obvious, yes? The two players play. Well, if I use the notation from the first slide, this A0 should be the weakly initial object, yes? But it doesn't matter. I mean, Eve could start from this and already choose some transition to A0, yes? So in any case, the two players alternately choose transitions building a sequence, yeah? Building an infinite sequence. And Eve starts the game, yeah? So it is not like Mazur wanted. Mazur was not a gentleman, this is. But so in any case, Mazur played with intervals, open intervals in the real line. And here we play with very abstract objects. And this game definitely exists. It's well known in model theory. In category theory, I'm not sure whether any people except me actually studied this game. In any case, you see, this game is now only for fun, yes, because we do not know who wins, yeah? You see, so something is missing here. I mean, the definition makes sense, definitely, but one parameter is missing, yes, because by this way we play and nobody knows who wins. So, now here it comes. So the second parameter, so sigma k, is and from now point I will always assume this. I mean that the category or this evolution system is contained in a bigger one, in a bigger category where every sequence converges in this bigger one. And let's assume, which is not written here, but let's assume that the objects of sigma k are precisely the limits of sequences in k, yeah? Not to make it too large. And yeah, so that's it. And from this point on, we can really say who wins in this game. So we fix an object which is a possible limit. I will try to avoid this technical word co-limit, okay? Why co-limit? Because there are two dual concepts in category theory. Co-limit of a covariant functor and limit of a contravariant functor. But since I'm not going to consider explicitly contravariant functors, so I will say limit, yeah? And it could actually be some more abstract, some operator which assigns to each sequence or evolution, it assigns some object plus some arrows, etc. But so let's, in practice, this will be really concrete situations. So now we say that the second player wins if the limit of this sequence, okay, remember this is my notation, yes? This A vector denotes the sequence, yeah? I mean, this, where the objects are capital A and so the second player wins if the limit of this sequence is isomorphic. This thing means isomorphic to U, yeah? Not equal. If you say equal, it would be really made no sense. I mean, category theory, after all, is about isomorphic objects, yeah? So otherwise, if wins. So that's the definition of the game. So now coming back to the history, yeah? So Mazur invented this game to study small or large subsets of the real line. Namely, okay, I can draw it, yeah? He fixed some x in the real line and played with intervals, yeah? Smaller and smaller intervals, and the second, actually he claimed the first player wins if the intersection contains some point from x, yeah? And he asked how can you characterize the existence of a winning strategy? So the game is may not be determined, yeah? I mean, it's a Bernstein set or whatever. Well, so open intervals or open sets of a fixed topological space, this is a partially ordered set, yeah? So after all, it's also a category. So it is a special case of this very general setting. However, you know, and if you are interested in the point, well, we would have to say that all points in X are isomorphic, yeah? And all points outside of X are also, or whatever, are not isomorphic to those. And then this works, but it's not particularly interesting for me, at least. But okay, of course, this topological Mazur game is quite important, and yeah, there is this, in this particular setting, the second player has a winning strategy if and only if this contains a dense G delta, yeah? Absolute G delta. This is what Ox-Tobbe's theorem. But I'm not going to talk about this. So this game now this really makes sense. You have two parameters: the category you are playing with and this object from outside. From outside of this category K. Now, so this is my invention. We call this object K generic or generic over K or with respect to K if Ott has a winning strategy in this game, yeah? Well, so maybe you can argue, but I do not see any problems with generic filters, yes? So the idea comes from forcing, after all, where you also introduce something extending the universe. So here K is the universe, and you have to extend K to sigma K in order to talk about new objects. So yeah, what is a strategy, I should say? This is simply a function which tells the player how to play, yes? So you have a finite sequence of arrows finishing with something, with some index an where n is even, yes, if it is about the second player. And it tells you what kind of arrow he should choose. So this is a strategy, yes, and it is winning if, no matter how if plays, the resulting sequence will converge to something isomorphic to U. So that's There are some variants of this, like Markov strategy. Markov strategy is a strategy which depends only on the last move and the number n, where, this is this n play of the game. And stationary strategy, or a tactic, which depends only on the last move. So, but I'm not going to discuss this. There are some open questions. I mean, in the concrete examples, there is a winning strategy. Does there exist a stationary one or whatever? But that's it. Yeah? And all right, so this K-generic object is unique. That's the fact. Oh, I should speed up maybe. Okay, so why is it unique? So there's the proof. That's the proof after all. So, suppose there are two generic objects. Odd uses the strategy for the first one. But the rules are the same for both players. So if can use the strategy for the second generic object, yeah? Even in the first move, she would pretend that there was something before, and they both win. But the limits of the sequence, there is only one limit, so that's the point. So now let's go to You see, so in the title I had universality as universal objects. So that's the proposition. Actually, maybe I can quickly sketch how it works. So if you have the amalgamation property, then this generic object is universal in this particular sense. We think of the arrows or transitions that these are some embeddings, yeah? Because otherwise, in the category of all non-empty, say non-empty sets with all possible mappings, this proposition is definitely not interesting, yes? Because every set would be universal. But all right, so how does it work? We have this X, which is a co-limit limit of a sequence, yeah? And we play this game in such a way that the second player uses the winning strategy for you, okay? And the first player, the first player, yeah, if starts the game. So she could start with anything, with any A0 which has some embedding, yes, some arrow. Then odd, the second player responds with something. If makes the amalgamation with this and this, yeah? This is her response. All right? The amalgamation of this arrow and this arrow, and this is her response. And now you see how it works. This is E1. She continues this way. By this way, the limit or co-limit of these arrows is this E, which is on the slide. But generic objects exists without amalgamations, and then the universality fails very often. We'll see some examples. All right, so this is homogeneity, another very good property. So if K has the amalgamation property and we have this generic object, then, okay, this is what it says. Maybe there is some diagram, yeah. Any two embeddings of a single object extend or are conjugate, yeah, by automorphisms. It's usually better to waste this paper. It's better to imagine it this way, that this is this generic object and you have one copy of A and you have another copy of A. And you have an isomorphism. So what does it mean? You embed A to A0 and then the other embedding goes through the isomorphism. And then it really extends to an automorphism. This is what it says. So some people call it ultra-homogeneity, whatever. Especially in topology, homogeneity is usually thought of as, for every 2 points, you have a homeomorphism moving one point to the other. Yeah? So here it is with respect, we do not have points after all, yeah? So with respect to K. So this is a very good property which again can fail in this general setting, but very often it holds. All right, yeah, so this is a very technical property, but I'd like to, I need to mention this because on one of the next slides there will be some theorems which involve this. So the weak amalgamation property. And yeah, so it's pretty technical, yeah. It's was discovered by Alexander Ivanov, currently from Gliwice, formerly from Wrocław University. And he was studying the existence of generic automorphisms of omega categorical structures, yeah, so in model theory. And he discovered this property, and so some of the results are joined with Adam Krawczyk, where we rediscovered this property. So it says that you have some state Z. Maybe you cannot amalgamate any two transitions from Z, but there exists some transition, some very special transition to Z prime, with the property that any further could be somehow joined together, but you know, they coincide only on Z, not on Z prime. So let's see the diagram, yeah? Okay, because what you may, if you don't read it carefully, you may think that this is cofinal amalgamation, but cofinal means that you can always extend, every object can be extended in such a way that any two transitions could be amalgamated, okay? Let's don't read it so much. Here is a picture, okay. So you see, cofinal amalgamation property means that you start with Z, you can extend it to Z prime in such a way that for every Fg, you can close the diagram, yeah? That's very natural. And weak amalgamation tells you that this square may still not be commutative. I mean, only going through from Z. Yeah, E composition F composition F prime is the same as E composition G composition G prime. So that's the difference. And I would be happy to get some examples of natural examples of classes or categories with the weak amalgamation property and not the cofinal one. There are not so many. I mean, we have continuum many examples, but they are more or less of the same nature. Finite graphs with special properties. Okay, so in any case, here are two examples of classes with the cofinal and not with the amalgamation property. So, finite cycle-free graphs. Well, so if you have such a graph and suppose it is not connected, okay, because the class is hereditary, yeah? So if you have two components at least, maybe more, I'm showing why there is no amalgamation property. You choose two vertices and you extend by this way. This is one extension, call it X, and the original graph is Z. And then take another extension like this. This will be Y. No matter how you amalgamate, you get a cycle, yeah? So this cannot work. However, if the graph is connected, this single component, and you extend it in two ways, you simply take the union with no extra edges and it has no cycles. It's an easy exercise. So it has the cofinal amalgamation property because every finite cycle-free graph could be extended to a connected one in the same class. The second example is, well, the number 2 could be replaced by any finite number. Things become a little bit more complicated, but still doable. So, and this example shows that I can actually show you quickly that the generic object exists, yeah? So let's look at the second example. So what are possibilities? So triangle, yeah, it's of degree 2, and square, pentagon, etc., yeah? repeated infinitely many times. All right, so I claim this is the generic graph with respect to the category of finite graphs of vertex degree not exceeding 2. Why? Suppose, so imagine we play this game. If gives me some finite graph with this property. So it has, some of the components are of this form, some other are simply lines, yeah? I mean finite lines. So what I'm doing, I'm odd now, yeah? I'm closing each line by adding one more vertex, and if it is remove number 2018, I should make sure that there are 2018 triangles, 2018 squares, etc., yeah? Up to 2018 polygons, yeah? By this way I win. So, and you see, this graph does not contain the integers as a graph, yeah, where which consecutive numbers are connected. But the integers come as a limit of some sequence in this category. So this graph is not universal, still generic. Okay. So here are this, so I'm sorry, this is a topological conference, but the main results, more recent results, which I mean, with some other are really in model theory. So we managed, with Adam Krawczyk, we managed to characterize the existence of a winning strategy. And it turns out that the weak amalgamation property is crucial. So, well, yeah, but this is in the case of a countable category. So countable means up to isomorphisms, there are countably many objects and countably many arrows, transitions, or whatever. Directed means, in model theory, joint embedding property. I mean, you have two objects, you can find two arrows going to the same one. Where actually in my setup, if I set evolution system, I could have deleted directed because then it's automatically true, almost, yeah. So, not completely, you need some amount. But in any case, so in this particular setting, this is the result, that the weak amalgamation property is the minimal requirement which works, and moreover, the game is determined. Either there is this generic object or if wins always, yeah? Fine, I have some 15 minutes, I should speed, why I called it this, okay, never mind. Yeah, examples of generic object, that's the point. So Cantor seems to be the same. Maybe Euclid, but I don't know. Cantor is really, this is actually the motivation for studying this kind of phenomena. Yeah? Cantor really proved that if you have a countable linearly ordered set, which is dense, no endpoints, then it is isomorphic to the rational numbers. Yeah? So, and in this terminology, it is generic. Yeah? All right, next, maybe I missed something, but this, according to my knowledge, is Urison. Was kind of forgotten for many years. Now it's quite popular because of topological dynamics. So there is generic Polish metric space. Polish means separable, complete. Yeah? And it's really strongly homogeneous. This homogeneity, which is written here, actually extends to compact subsets, which was done much later by Hunaishvili, some Georgian mathematician. So in any case, I also have some paper with Matti Rubin where we prove homogeneity with respect to Lipschitz mappings. Yeah. Anyway, that's it, and definitely it would not be honest not to mention Fryset. Roland Fryset was a French mathematician working in theory of relations, actually model theory. Yeah? So this is really the main thing. Yeah? So typically these generic objects are called Fryset limits However, according to Freise, amalgamation property is assumed. Yeah? And okay, so the setup is this. Yeah? You have a class of finitely generated models. Freise actually considered finite only, and he did not, because he was in theory of relations, so models with relations only. So finitely generated means finite. But if you allow algebraic operations, finitely generated models could be quite big. Yeah? And the joint embedding property, as I said before, you have two models, you can embed them into a single one. Yeah? And the amalgamation property, you know. And being hereditary is category theory does not see such a property. And indeed, this property could be deleted. However, if you have this assumption, you have some nice correspondence between the class, which is called the Freise class, and then the Freise limit. So it is a model which is countably generated. Every finitely generated submodel is in K, up to isomorphisms, and then it is homogeneity. And the model is characterized by some extension property. So this is already classical. I mean, take any reasonable textbook in model theory, or maybe any textbook in model theory, you will find a chapter on Freise limits. And if not, means that the book is not good, definitely. So, yeah, so again, this is the Freise limit of finite linearly ordered sets. The Rado graph, this is something, I will not tell you the details because of time, but it's a generic graph. Actually, Richard Rado defined it completely independently from the work of Freise. It's a graph on the natural numbers. You take a natural number n, take its binary expansion, and you connect it to smaller numbers whenever there is one in this expansion. And this is, okay, but I don't have time to draw the details. And now, Philip Hall, he wrote a paper on in group theory where actually he managed to somehow to produce this generic locally finite group without proving the amalgamation property directly. And homogeneity of this group is that every finite isomorphism actually extends to an inner automorphism. It's a very nice example. Yeah, the last one is probably not very well known. You take infinite cyclic groups, actually with only one, the integers. But there are many embeddings of the integers into the integers. And when you produce the generic sequence according to the game, let's say, you receive the group of the rational numbers. This example shows that you may have a monoid or originally, and you receive something really new. Okay, so that's another example in this spirit. Take all continuous surjections of the unit interval, and so forget about Freise limits now, yes? Let's come back to these generic objects in terms of the game. So it turns out that, the pseudo-arc is the generic space. So I have to give the definition due to Bing. So what I'm working with my younger colleague Adam Bartosz, to find a better proof of this, this fact, because this definition is really a theorem. So chainable continuum is by definition the inverse limit of intervals. We are working here in the category where we have continuous surjections and the arrows are reversed. So, of course, inverse sequences, not direct sequences. And And Bing's theorem says that if you have a hereditarily indecomposable continuum, which is inverse limit of intervals, it must be homeomorphic to the pseudo-arc. I mean, there's only one. And knowing that the pseudo-arc is generic, yeah, there should be some better proof of Bing's theorem, but we have some troubles with that. Okay. In several other cases, okay, I forgot to mention it on the slides. I have a paper with Ola Kwiatkowska where we really proved uniqueness of something. So let's see, maybe I have it. So one more example, because the time is passing. I have like 9 minutes, right? Or 8 minutes. Manolo, are you sleeping? 8 minutes, yes. The Cantor set is generic, yeah, but okay, there's nothing special. Use stone duality, go to Boolean algebras, and then when you get the Freise limit. Oh yeah, so I mentioned, I have it, fortunately, I already forgot that I had it. So, yeah, so the Poulsen simplex. So I'm already moving to functional analysis. This is a unique simplex in the separable Hilbert space with the property that the set of extreme points is dense, everywhere dense, really. And uniqueness of this simplex was an open problem for some time. And the proof of uniqueness provided by Linden, Strauss, and some other people cannot be called elementary, definitely advanced. And we have a really elementary proof which takes half of a page. Yeah? Okay, what's the category? So you start with a zero-dimensional simplex. Then you obtain one-dimensional simplex. This is very easy now. But how do you obtain a triangle? You simply think of it that this is some material, some elastic material, and you try to push it up and make a triangle, but you remember where you started with. So this is this affine projection which goes back. And then you continue, you choose a point in the triangle and you make this three-dimensional simplex and you remember where it goes back. These are the projections or the surjections, affine surjections. That's how it works. And yeah, so the idea, the uniqueness is, okay, so this is the result, that the uniqueness of the Poulsen simplex is proved more or less by this way. You take a simplex whose set of extreme points is dense, represented as the inverse limit of such a sequence, and you prove that the sequence is generic, I mean, has this absorption property. That's it, and it takes half of a page only. We have another result concerning the so-called Lelek-Fenn, because practically the same. All right, but as I promised some universal topological vector spaces, so I have to talk about it the last 5 minutes. And yeah, so there is a generic separable Banach space, denoted by G. Why? Because this was the so-called Gurari space. And you see, I like this result because you can explain it to even undergraduate students, I guess. I mean, what they need to know what a normed space is. They need to know what an isometric linear embedding is, and that's it. The knowledge of functionals, dual spaces is not needed for that. Yeah. They only people need to know what a normed space is, finite dimensional normed, and then you can explain the game. And then you can say, okay, there is one space where the second player has a winning strategy in this game. And so this space was discovered by Gurari, and he wanted to solve this Mazur problem on rotations, which is still open. It asks, okay, you have a separable Banach space with the property that for every two vectors on the unit sphere, there is a rotation, a linear isometry moving one to the other. And is it necessarily isometric even to the Hilbert space? Because there are no other examples. So, as you may guess, Gurari did not solve the problem, but his space has this property approximately. With epsilon errors, you can do it. And you see, look, Gurari's paper is in 66. Uniqueness of the Gurari space is 76. So 10 years later, using really advanced methods, the method of representing matrices by Lazar and Lindenstrauss. So it really cannot be called easy, this proof. Uniqueness, I mean that you have Gurari had some property which defines the space, yes, and some extension property. And he could prove that the space is unique up to isomorphism. But uniqueness up to isometry was an open problem for like 10 years. And it took quite a lot of time to find a really elementary proof. So I have a paper with Sławek Solecki where the proof is completely elementary. I mean, we could have simplified it even more because the crucial lemma which we have involves functionals, okay? The definition of a suitable norm involves functionals. Later, we discovered that it could be even simpler, but in any case, you can see that it is a simple proof. Okay, and if you combine it with this work, with this theorem, yeah, so I met Felix Cabello Sanchez later, and Joanna Garbulińska-Węgrzyn was my student that time. So we found that it can be generalized to quasi-Banach spaces. Well, you may find it really extreme and not interesting at all. However, what is in this paper, okay, I do not have the bibliography, but you can find it by these names. And where p equals 1, this is still about Banach spaces, yes? And so we found that there is a generic separable p Banach space for each possible p. And what is a p norm, p Banach set? So I have this definition, yes? Apparently these spaces are important in application. It's outside of Banach space theory, yeah? But still. So you replace the triangle inequality by this thing, yeah? And P Banach space means complete with respect to this. This is from this P norm you get a metric, so you get a topology, etc. Yeah, and it turns out that if P is strictly less than 1, it was not known whether there exists a universal separable P Banach space. Universal with respect to linear isometries. So it was really a new example. We also have some result on universal operators on this space GP, which as an application, it tells us that GP plus GP is isomorphic to GP, which was not easy to obtain without these universal operators, because you see, GP, the dual is trivial if P is less than 1. So there are no methods like in Banach spaces. Anyway, so that's the result, and yeah, so it's really universal, yeah. And the last one, I guess that's the last slide, because I'm supposed to finish. So there is a separable, generic separable graded Fresher space. So again, you may find it interesting or not. For me, the good point about it is that we first had to construct a universal operator from the Gurari space to the Gurari space. This is a joint paper with my former student, Joanna. And we used this operator, elaborated it, and from this we produce this generic inverse sequence. Okay, a Fresher space is nothing but inverse limit of a sequence of Banach spaces. And this graded makes it makes it more complicated, of course, and it has a nice homogeneity property and universality, etc. but I'm seeing a yeah. Okay, so the last thing is that LP is generic. I do not put any names. I do not claim it's my result. I worked on it with Tomasz Kania. However, Jordi Lopez Abad with some co-authors also has this, so it's better not to put any names. And I finish with this open question. I do not know any other examples. So thanks for your attention. Yeah.